So let's consider two beakers full of water. Okay, I want to take these two beakers of water and I want to actually add them together. Now, one of these beakers of water, I'll give you some of their properties. One of these beakers of water is 100 grams, and it's been observed to be 50 degrees Celsius. And the other container of water is 500 grams, and it was observed to also be 50 degrees Celsius. And so all that means is that I have these little particles inside. And if I were to zoom in, if I could zoom in this far, I'd see them zipping around. And the average speed of the particles in this container would be equal to the average speed of the particles in this container, which means that their temperature is considered to be the same. Okay? So let's make a note of that. Let's call this container 1 and this container 2. I could say that temperature 1 is equal to temperature 2. Silly observation, but I can see it. Now I know that these guys, if they pour together, well, maybe you can tell me, if they pour together, what would you expect to find? Yeah, 600 grams at 50 degrees Celsius, because the average of these two like temperatures, 50 degrees Celsius. Makes sense. So 50 degrees Celsius, 600 grams. Now that tells me that the temperature, or temp 3 is equal to temp 2, which is equal to temp 1. That's great. However, what we said before, something about thermal energy. What we said about thermal energy is that it's the total kinetic energy and potential energy of atoms and molecules in a substance. So the total kinetic energy is heat. Let's take a look at this again with that in mind. The total kinetic energy. Which one has more total kinetic energy?
Beaker 2.
Why would you say, how about we raise hands? Why beaker 2? Yeah. Yeah, it's got more stuff, more mass. So if we're talking 1/2 mv squared as kinetic energy, I would say this guy's got more mass than this guy. So I would have EK larger. Or I could say, instead of saying EK, let's do it a little bit better. Let's stop talking in terms of kinetic energy. Let's talk about thermal energy, or heat energy. So EH is larger. Recognizing that thermal energy is really just the total kinetic energy for all the particles, if we add up all the particles. And so this guy's EH would be smaller. On this page, which container of water has the most thermal energy, or heat energy? Yeah. Yeah, beaker 3. Let's say largest. It's got the most thermal energy. So I can say that beaker 3, the combined beaker, has the most thermal energy. Does that say anything about its temperature? Not necessarily. But it certainly has the most thermal energy. Let's think about lakes. You guys know something about the Great Lakes. Which Great Lake has the greatest potential to hold thermal energy? Why? It's the biggest, yeah. So which one keeps the land around it the coldest in the summer? Lake Superior. Which one has the least capacity to hold thermal energy? What's that? Erie, yeah, it's the smallest volume. And actually, which one's, I should say, which one's the most likely to freeze over?
Erie.
Lake Erie, most likely to freeze over. It's got the least thermal energy being held into it. Actually, it's going to be the quickest to lose its thermal energy in the wintertime. Okay, but it's this sort of idea. It's not necessarily any hotter, although often it is, but that isn't what keeps it. Actually, you'd think it actually heats up the most in the summer, which might make you think it's least likely to freeze over in the winter. But the fact is, its temperature swings so wildly because it has less particles.
Its temperature is easiest to change because its mass is low.
Beautiful. Yeah, very well said. Easiest temperature to change because its mass is lower.